In this video, we're going to explore three problems that occur in the design of a supply chain network. We discussed those in class. However, I didn't have a chance to demonstrate them yet in Excel, how we could actually solve them. We'll use XLOM to actually solve these three problems. The first one is the sort of gravity location problem. All right, so gravity location. Well, actually, it's a location problem where we're using the gravity method. And essentially, what you want to do is that if this is a grid and we have a number of customers, we're trying to find what is the best spot to locate the facility so that the sort of weighted travel to these various destinations is actually minimized. So how can we do that? Well, what we would actually like to do is to minimize the sum of the weighted distances, all right, the distances are calculated from the facility that is located out to those customer points. So typically what we would have is a set of coordinates, x, y coordinates, and we would have that for each customer. So we could have customer 1, for example, would have x1, y1, customer 2, x2, y2, customer M, xm, ym, and so on. So these could be the coordinates, and then we could say, let us locate the facility at x0, y0. So if we do that, the distance between the facility and any one of the customers, so for example, let's say the distance between the facility and customer 1 would be calculated as follows. It would be x1 minus x0 squared y1 minus y0 squared, and we take the square root of that. Essentially what we're doing is we're finding the distance along the hypotenuse. If you were to draw a right angle triangle, then you're trying to find that distance of the hypotenuse. So given that distance now, if we, depending on where we locate the facility, those distances actually change. All right, and so essentially, as I mentioned, the problem is to minimize the weighted distance. The weights will typically be, it could either be how many trips we intend to make back and forth between the two locations, or the total volume of product that we intend to ship from that facility to the location. So you want to consider the weight in that fashion. Either number of trips, so the weight could be number of trips, or it could be, the weight could be the total annual shipment. All right, so that's the first model that we're thinking about in terms of the location of a single facility for a group of customers using the sort of gravity location method. All right, the second issue is basically a basic transportation problem. So I'm just going to sort of block out the space right here, and we have a transportation problem. And that transportation problem essentially requires that we go from a number of suppliers to a number of possible customers. So say we have 4 customers and we have 3 suppliers, 1, 2, 3, and essentially each customer has a demand. So we have could have a fairly dense network here, where every supplier can supply every customer. So we have supplies at this location, and then we have demands at this location, and then there's a cost Cij, which is basically the cost of going from supplier I to customer J. And the model looks like this: minimize for us the sum of the shipments. Xij is the amount that is shipped between facility I, warehouse I, and customer J. Then we must make sure Xij, that if all of the amount of material that is shipped out of a facility I must be less than or equal to its capacity, and then the amount that is shipped from all facilities to a customer J must be greater than or equal to its demand, and we simply need Xij to be greater than or equal to 0. So that's the basic model, right? And that's a transportation model. Okay. The last model that I wanted to talk about is essentially a plant location model, or warehouse location, plant location, or we could say a warehouse location model. In which case, now it looks very much like the transportation problem, except that now we going to decide which of the plants are going to be open. Not all of them necessarily have to be open, or which of the warehouses. So we could have, like I said, the same kind of construct that we have over here, but we could decide that not every one of them needs to actually be open. Okay, so in a case like that, what can we do, or how do we make the decision around which of these to keep open? All right, so let us discuss that a little bit. Just going to make sure that this fits properly. Okay. There you go. It's a little big. Okay. So let's open a new sheet. Give myself some space. We don't have to save that one. There we go. So, in the warehouse location problem, so what are we looking at? Let us define the following. So we're going to have some fixed costs associated with, that's like a fixed cost with opening a warehouse, and then we will have essentially SI as the supply, we'll have DJ as the demand for each of the customers, we'll have XIJ as the amount shipped from I to J. Then we'll have a variable yi, which we'll say is containing 0, 1, which basically means that is 1 if warehouse is opened. Alright? So it will be 1, otherwise it's 0, otherwise. That's what we have there. So if we want to model, and then we're going to let M be a large number, a large value, and M could basically be the we could pretty much set M equal to SI. It doesn't hurt. So our formulation looks like this. Minimize sort of the transportation costs. So what I guess what I'm missing here is I need your CIJ, which would be unit transportation costs from I to J. So in this case I'll have CIJ, XIJ, so that's my transportation cost, plus I need to include my fixed costs overall I. So that's the fixed cost and that's the transportation cost. Subject to, of course I want to satisfy my demands, so overall I, this must be greater than or equal to the demands at a given customer J. Overall J, Xij must be less than or equal to the supply, I. And this is where we need a logical constraint. So I'm going to take Xij, and this would be all of the supplies out of warehouse I over all customers minus M times Yi must be less than or equal to 0. And this is called a logical constraint. This is logical constraint. And what it does is that it allows us to say if this at all is positive, if this is positive, then the this part right here, for this equation to be satisfied, the y must be 1. It cannot be 0, because if it's 0 and this is positive, then that constraint is violated. So in the optimal solution, MYI must be a positive value which is larger than this portion, so that the constraint can be satisfied. And that's where the logic actually comes in. So we simply put Xij greater than or equal to 0, Yi is contained in 0 and 1, and it's binary, right? And that is the warehouse location problem. So I'm just going to demonstrate briefly for you how we would solve those in Excel, OM. But you certainly can do it in Excel as well, manually, that is. All right, so let's just go and take a look at Excel and see what we got there. Let's just look at the gravity problem, and I have actually already entered all of the data, but I think it's fairly easy to understand how we put it all together. All right, so if we look at this carefully, what happened is that we have 5 locations, and so for each location the weight could be the number of trips, as I mentioned. So if we're expecting 200 trips from to location 1, 150 trips to location 2, and so forth, and these are the coordinates, right, on an XY grid. So 5, 10, 10, 5, 0, 12, 12, 0, and then add 8, 4. So we could take the average of the X values and the average of the Y values, and we'll get these 2 coordinates right here. So that's one thing that can be done. But the way in which we would try to solve this problem is to try to minimize the weighted distances. All right. So of course we would need to calculate the actual distance of each of these points from the coordinates of the facility, and then attempt to minimize that. This is Excel OM, so all of the sort of the macro is already written for this problem, and we could see a graph of it right here. So apparently this is where we would locate the facility, and that sort of minimizes for us the weighted distance. Now you could see the size of this indicates the number of trips. So clearly, there would be a tendency to want to have the facility located to the point where you expect to get the largest number of trips. Okay, so it's not surprising that we're sort of located pretty much at this point right here. So that's the sort of gravity location problem. Let's take a look at a transportation problem. So with the transportation problem now, I don't have a graphic of that one, but I think it's not too hard to appreciate, which is that I have here a number of origins, and so these origins are essentially my warehouses. I could call it warehouse 1, warehouse 2, warehouse 3. And then my destinations are essentially my customers, which I could rename customer 1, customer 2, and so forth. Customer 3, customer 4. All right? And so this matrix right here, we would simply supply cost information. And that would be the cost of shipping 1 unit from warehouse 1 to customer 1. 1 unit from warehouse 1 to customer 2, 56 cents, 22 cents, 4 cents, and so forth. So we'll have that information right here. This part is the supply from each of the warehouses. So warehouse 1 can supply 10,000 units, warehouse 2, 15,000, and so forth. Okay. Now what is the demand at the customers? So we place our demand at this point, which is 8,000, 10,000, 12, and 9. So customer 4 wants 9,000 units. The decisions that we're going to make are actually right here. I could just highlight it for you so that you could see. And so we will decide how much warehouse 1 will ship to customer 1, and so on, warehouse 2 and warehouse 3, and of course we repeat that for each customer. Of course, it's not easy to know this ahead of with some simple formulas. There is what you call a particular algorithm called a northwest corner rule for transportation problems, but Excel could actually solve that problem for us relatively easily using a macro that has been designed for that purpose. All right, so we're going to focus on that using the macro. So the macro actually is Solver. I don't know how many of you are familiar with Solver, but if you are not familiar with Solver, what Solver does for you is that it will take a spreadsheet, and of course the spreadsheet has some objective function in it. There's something that you want to maximize, minimize, or you're trying to get a particular value, and that value is connected to a number of decision variables. So in our case, the decision variables are how much to ship right here, and the objective function is the cost. We want to minimize the cost by changing the values of these cells. But then we may have some constraints, and we need to specify them. So here's how the problem is. Set the objective B25. Well, that B25 is this value right here. Right now it's set to 0. And then we want to minimize that objective function by changing which cells? These values right here, sorry, from B20 down to E22. That's the ones that we want to change. So what we would do is we would simply go in here and select the cells that we want to change. Select that, that's all. Okay. Now we need some constraints. Well, what are the constraints? Since we have the demands right here, we could sort of tally below here the actual amount that is supplied to each customer. So that would be our supply totals right here. And then we could tally over here, that would be the demands that we satisfy, and over here what we actually shipped out of the warehouses on this side, row total, column total. All right. So that's what's shipped out of the warehouses. That's what's received by the customers. Okay. And then we want to make sure that the amount received by the customers is equal to or more than what is actually demanded. So that's where this constraint comes in. This constraint ensures that the amount that we receive exceeds or is equal to what was demanded. The second constraint, and how you would specify that, is you would say that the amount that is shipped, which would be this total right here, must be less than or equal to these values right here. Okay, so that's how we specify that. If I were to say change, it comes up, but I'm not going to change anything. I'll just sort of show you how we do it. If I remove this, so it would be the amount that is actually shipped, right? I select those three, must be less than or equal to the amount that we have available, which would be those three right here. Okay, we would simply say okay if we have everything that we need, and we're told to make unconstrained variables non-negative. So in other words, we don't need to specify that these values are non-negative, which is how much is shipped. You cannot ship a negative amount. Because this is a linear program, we could select a number of different approaches to solving this. Some nonlinear approach, linear, simplex LP, and evolutionary. So because this is a linear program, we will select simplex LP and then we simply tell it to solve. And it should come up with a solution. It's working. And there we go. Voila. We get this dialog box that says, we found a solution. Do you want us to keep it? I will say yes. Now, we're not always sure if it's optimal, but in this case, we could pretty much assume that it is. Let me just widen the value and see what our cost is. $13,830. So we would ship, as you see, from customer 1 would receive his shipments from warehouse 2 and 3. Customer 2 will receive from warehouse 2. Customer 3 from warehouse 1 and 3. And customer 4 from warehouse number 4. Okay. Generally speaking, the way in which linear programming works, it will attempt to find a solution where it will each customer will receive as much as possible from a single supplier, and exhaust that. So whichever is bigger. So if the demand from a customer is less than the supply, it will try to receive everything from a single supplier. So you could see here customer 1 receiving all of his shipment from the warehouse number 2. We see customer 4 receiving all of his shipment here as well. But 3 and 1 had to have theirs broken up. So, sometimes you have to split the shipments. But in this case, we got the solution, which looks pretty good, and that problem was relatively easy to solve. So that's a transportation problem. Let's look at the last one, which is a facility location problem. So I'm going to explain this model. I'm just changing some values, and I'm going to just reset some of these values right here. Just clear them for now. We don't want to bias things, so we're going to remove that. Let's just clear those values because I had to test it before. So clear the contents. So I took the very same transportation problem, but then I changed it to a location problem. Why? Because I changed the quantities that are available at each of these locations such that not all of them have to be active to supply the demand. The total demand is 39,000. But if you look at that demand, it could be satisfied by plants 1 or warehouse 1 and 3, see, for a total of 19, or it could be supplied by 2 and 3, which would exceed the 39, or by 1 and 2, which would also exceed the 39. So we have some choices, but you don't have a situation where just 1 alone is sufficient. So it looks like we need at least 2 plants open. Question is, which 2 should we open? And then when we decide the 2 that are open, how should we go about shipping from those plants to the destinations? So let's take a look at this. So what I'm going to add now is that I have a fixed cost or fixed charge associated with each location. And here's that fixed charge. So if I'm open location, if I'm going to supply from origin 1 or warehouse number 1, I will incur a fixed charge. That means I have to establish this plan. So this is kind of more of a strategic planning problem where you have not actually decided which facilities you're going to open. But once you decide that, then you're going to have to build it. So maybe this is just a basic factory shell. 50,000 for 1, 90,000 for location 2, and 75,000 for location 3. The other variable I must introduce is whether or not the plant or warehouse is going to be open or closed. So I have to create that these variables right here. So here are the costs and here are the variables. What this part represents is the actual value of M times Y. In other words, M times Y. Remember that M, I'm going to use, for my value for M, I'm actually going to use the supplies at the location. If you may recall, from here, I said that I was going to take M as a large value, and that value of M was essentially going to be the supply at the facility. Okay? Because you could never ship more than that quantity out of that facility. So if we go back here, if we look at this value, the way in which what I've done is I've taken this value right here, which is the value of the decision variable, multiplied by its corresponding supply, which is the M value. So because it's 0, 0 times 20,000 is 0. 0 times 25,000 is 0. Now if I made this 1, which meant I open warehouse number 2, you will see that that value of M times the decision variable is now 25,000. All right, 25,000 from here. And our constraint that we require for the logical variable is that this part must exceed the total amount that is shipped out of that location. It must be equal to, right, or greater than the amount shipped out of the location. So these are the amounts, the row totals are the amounts shipped out of those locations. So that helps me now to take care of this constraint, which was not in the transportation problem. This constraint right here. Okay, so I need this term, and then I need this, which is the total amount shipped out of warehouse I, and this is the large number M that forces the warehouse to be open if I'm going to ship out of it at all. So if we go back here, that's taken care of. And so essentially these are the constraints that I have to put in. The other thing is that I must also determine how much fixed cost am I incurring. So if this is open number, which is warehouse 1, then I must multiply by the fixed cost for warehouse 1. The warehouse 2 times the fixed cost of warehouse 2. Warehouse 3, fixed cost of warehouse 3. So that is, I'm capturing that cost right here. So I could call this the fixed cost. And that fixed cost I'm going to add now to the transportation cost. So now I have my total cost right here. Okay, so I could actually identify transportation costs. And it would just simply be the sum product of these values with these values. Alright, and so I could have said my total cost right here is the sum of my fixed cost plus my transportation costs. But it's actually captured over here, so I don't really need to do it twice. Just wanted to show you that you could actually break it out a little bit and then capture it in a total. Alright, so then I could essentially take this total cost and sort of move it over here. Alright, cool. So it's just the sum of those two things put together. And I guess we could just go ahead and solve our problem. Now remember, I had to add some constraints. Oh, last but not least, I have to make sure that these variables over here are binary variables. What I mean by that is that they're 0 or 1. Right? I'm going to just set it to 0. So we're starting from scratch and we're going to see what happens. So let's go to the solver. And if you look at solver right, well, what I've added would have been that in terms of the decision variables, I want to change the shipment variables, but I also need to consider what the decision variables around whether or not I have a plant open or closed. So that's added in here. Then also I need the constraints that reflect that these values right here, which are part of the logical constraint, those values, as a large number, is greater than or equal to the supply. And then last but not least, that my decision variables for plant opening or closure must be binary 0 or 1. Once I've done that, all I have left to do now is to solve the problem, and it's working, and away we go. Here we go. Voila! I found a decision which basically said open plants 1 and 3, which would have a total fixed cost of $125,000, but my transportation cost would be $17,460. And you could see origin 1 would ship to destination 2, 3, and then origin 3 would ship to 1, 2, and 4. So the total amounts shipped 20,000, 19,000, 39,000, which balances nicely with the original demand of 39,000. And so that is the plant location problem. Quite, relatively easy to do in a spreadsheet environment. Okay. Of course, we have other types of models that include transshipment, and those could become even a little more complex. We have production planning models too that could be part of the design, multi-echelon supply chains. So we could definitely use optimization to help us make the right decisions around where to locate facilities. So this was just a demonstration to show you how we could use XLOM, or just Excel, to solve these network design problems.